All right, just looking ahead a little bit, we're going to finish up our introduction of the rate constant K today and look at a couple of examples of it. We're also going to link it to all the other Ks that we learned about last week. So there is a relationship between the two. They're not equal, but they are related. We have a lot of Ks floating around. So all of the reaction rate Ks are the lowercase Ks, which I write like that, which looks like a K. All of the equilibrium Ks, all the Ks that you would have learned from last week. So anything to do with the Gibbs energy, so K, K0, K1, K2, or any of the other ones like Kp or Kx, those are all uppercase. Now that we have to have equations that have both of them, I need to be able to tell you which one is which. And so the way that I will denote those two is between a lowercase k that looks like the one on the left. My uppercase k's are going to have little caps on them. So these are all of the k's that have to do with rates. The uppercase k's, the one like this, those are all to do with equilibrium k. So there's an example of an uppercase k again. I don't really mind how you do it in your notes as long as you can keep them separate, but that's what I mean when I have those two. So the big K, the uppercase K, is the equilibrium K. The lowercase k is the rate K. Remember, the equilibrium K, it's not just the overall K, but it could be any of those Ks associated with it. So things like K0, K1, K2 would be in there. Any of the other ones like Kp would also be in there. So all those subscripts are still there. All those Ks that we learned in the first week, those are all uppercase Ks, which I think if you watch that video again, you'll hear me talk about the two Ks. All of the other Ks that we have are the lowercase Ks. You probably won't see but about two of those. There's usually one called Kf and another one called Kr. And we'll introduce the difference between those two today. Okay, so just a little bit of nomenclature to clear up. The last expression that I think we had left with, we were kind of talking about, actually let me leave that up in case you're still working on it. The last one that we had left off with was that the rate constant K had this Arrhenius form of capital A times the exponential of minus E sub A over RT. And we had talked a little bit about where each one of those terms came from, what their approximate interpretation can be. That should really be a little bit closer, like here. So let's see how we use that. Often I can give you one of two pieces of information on these problems. I can either give you the K itself, or I can give you the A and the EA. When we get into next week, when we start to deal with the effects of temperature and how temperature changes within a reactor or during time, usually I will give you the A and the EA because that's how you can determine the temperature dependence of K, which we had mentioned yesterday. If you increase temperature, you should always increase the lowercase k. The rate constant always goes up if you increase temperature. The behavior of the capital Ks, those equilibrium Ks with temperature, those are a little bit different. In fact, I think we had briefly gone over that when I was talking about those Ks. The effects of pressure and temperature on those depends on enthalpy and stoichiometry. But the lowercase k, rate K, always goes up. So we've got that one. If you happen to know a K at a particular temperature, so if any K at some T, let's call it K1 and T1, not necessarily the F and the R that I mentioned before, just any arbitrary K that will subscript as 1, and you happen to know it at some particular T1, and the activation energy are known, you can always get the any other K at any other temperature by taking a ratio of those two expressions. So if you take K is equal to A exponential EA over RT and put that underneath another one, or above another one that looks like K is equal to A times exponential EA over RT, the ratio of those two will give you the new K. So if you take K2 over K1 and just use those definitions that we had, that's minus A times exponential of minus EA over R T2 divided by exactly the same thing except for T1. E minus EA over R T1. So the key point there is that the A's are constant. They're not functions of temperature. They always stay constant. Nor is E sub A. The activation energy is also not a function of temperature. And so if you take the ratio of these two, you end up with a fairly nice, well, maybe not nice, it looks very familiar, relationship between these two Ks. So the log of the ratio of K2 to K1 looks like minus the activation energy over RT1 times 1 minus T1 over T2, which looks pretty similar to something that we saw previously. Oops, cut it off. There it goes. That looks really close to the expression that we had whenever we wanted the shortcut K calculation. We had said if we ever know an equilibrium K at one temperature and the enthalpy of reaction, we could use an expression that looks like this. If you dig back, it was probably like lecture 3, I think, 2 or 3. We would have seen something like that. They're completely unrelated. There's no relation between the two of these other than they happen to share a very similar form. So try not to get them mixed up. This is talking about the relationship between two rate constant Ks. The other one that we had learned is talking about the relationship between two equilibrium constant Ks. But nevertheless, you can use this particular expression to adjust, well, that was a square. The rate constant K for temperature. And that's about the only expression that we'll ever use to adjust the rate constant for temperature. It becomes a little bit easier if I just give you the A as well. Then you just plug A and the EA into the Arrhenius expression, either one of those, A exponential EA over RT, and you just use that one to calculate K everywhere. Sometimes we don't know the factor A, but we do know activation energy, and so you end up with something like this. Either one of those is fine. It just depends on what information you were provided. Normally, if we had to figure out what those parameters are, the A and the EA, like I said towards, I don't know, the middle or something of last lecture, we can try to get kind of close if we go to PChem and take some quantum mechanics classes. We can try to figure out approximately what those are. Most of the time, those coefficients are measured experimentally. The way that we measure those things experimentally is we take the original Arrhenius expression, K is equal to A e to the minus EA over RT. If you take the log of both sides, natural log of both sides, you get that the log of K is equal to the natural log of A plus negative EA over R times 1 over T. And you've probably seen this sort of a relationship before in like a chemistry class, maybe not that exact one, but essentially what this looks like is a straight line. So if I call this Y and this B, which is the intercept, the slope M is equal to minus EA over R, and the independent variable becomes 1 over T. So you can see plots, or you can't really see them, you can make plots that look like this, where the x-axis is 1 over T, the y-axis is ln of K, and you can get data from some sort of an experimental system, which you will get an experimental system like that in your 176 class. We can measure rate constants in there for a degradation reaction. The slope and the intercept of that line of best fit through your data points, is related to A and EA by that expression up at the top. So if you ever have something like that, the process that's being done there to make that purple line, yeah, that's purple, is called linear regression. The easiest, well, I won't say, yeah, it's probably easiest at this point. If you've ever used Excel before and plotted something, or Google Sheets, I think, has exactly the same terminology. If you plot something and right-click on your data series, there's an option to say Add Trend Line. And the defaults of Add Trend Line are to do exactly that form. And so you can read the slope and the intercept right off of Excel that way. I can't remember if I have a homework problem that does that or not. At any rate, if you're not familiar with linear regression or the add trend line thing, your book has a nice little like 1-paragraph introduction to it. There's only a handful of steps, right? You plot 1 over t, you plot ln of k, you do linear regression, and out pops the 2 variables. So that's typically how those things are measured. They're not very difficult to measure. You run the reaction at a bunch of different temperatures and measure k, and out comes the A and the EA. So either it can be given to you in the form of like an A or an EA or a K, or I could give you a bunch of K versus T data, and you could do something like that and extract your own A and your own EA from it. I think the majority of the examples that I end up using are one of these two, right? Either I give you enough information to use this expression, or you just plain old have enough information to use this expression. But it's possible to do the other one based on experimental data, and that's where these numbers come from, is experimental data. The process of figuring that out takes a little bit of iteration, because as I said before, the general rate law, the overall form of R sub something is equal to K, for example, CA, CB. Whatever that form happens to be is determined experimentally. So not only are you determining that functional form experimentally, you then have to figure out what the A and the EA are experimentally. So it can take a while to characterize one of these reactions in a pretty quantitative way. That's why usually entire papers get published on like a single set of reactions, like 1 or 2 or 3 reactions that are important. And that's all they do in the entire paper is characterize it in this way. What's the rate law up here, and what are the rate constants down there? It takes a lot of work. Although if you're making up homework problems, you can just make up numbers, which is great, because I make a lot of homework problems. A couple of examples of various things that we can do with this. So for example, if I give you a problem that looks like the following. There's sort of a standard set of information that I can give you and a standard set of questions that I can ask you. Let's say that it's an elementary liquid phase reaction. And that reaction is 2A goes to B. And then I can give you a little bit of additional information. I can tell you the initial concentration of A is a mole per liter, or something else. The rate constant K, that's not minus, that's supposed to be a bullet. There we go. Is equal to something, 0.22. If you wanted, the most common mistakes I make in my homework problems, other than math errors, is messing up the units on K. I've gotten pretty good lately at checking them every time, but it's possible. So the units of K there are actually set. As soon as I assume that this thing is elementary, the units of K are also set, and I'll show you how those work out. And so those units of K have to match whatever the rate law is. As I mentioned yesterday, those units change, but depending on what that rate law happens to be. And then I could also tell you that the activation energy EA is 300 joules per mole, which seems kind of low. We'll have to check to make sure that's okay. Yeah, it seems okay. Usually those are on the order of kilojoules, but I guess I was just making up numbers here. Right, so that's kind of a standard set of information I could give you in a problem statement, and then I could ask you to find the following, which we will find each one of these. I could say adjust K for some temperature, so find whatever K happens to be at some new temperature, like 375 K. Oh, yeah, so that's another K. Kelvin K? I don't have another label for that, sorry. That's not the SI form, though. So the suggestion was put a degree on there. The SI unit for Kelvin doesn't have a degree. Tricky. Then I could ask you, find out what CA is at t is equal to 10 seconds, so time t, and t is equal to 375K. And then a last one, the same thing except XA, right? I want to know what the conversion is at all of these same conditions. Even if I don't ask you all three of those separately, I might just ask you the very last one, right? I might just say, what's the conversion of A after 10 seconds at 375K? You kind of have to work through most of those steps anyway, just to get to the point of being able to write the conversion. But most of the time, I will lay out both the homework problems and the exam problems in whatever the most logical way is, so that if nothing else, you can use some of the answers to either check later answers or help you along the way of calculating later answers. I would never ask for the reverse of this. For example, I would never put 3 in front of 1, because I think that tends to lead to people thinking of me trying to trick you in some way, which, you know, I will do, but not like that. So if we look at that first one, 1, not A, sorry. The question was, how do we adjust K for temperature? That always goes back to this one, ln K2 over K1. Remember, we're dealing with lowercase k's here. So this is EA over R T1. Let me make sure I wrote that right. Yeah. Times 1 minus T1 over T2. It's easy to mess up negative signs right there. I do it all the time. You'll probably see me mess up negative signs right there, but there's that handy rule of thumb, which is if temperature goes up, the K has to go up. So you can always use that as a check when you're done calculating an adjustment to K like this. If the temperature went up, the new K had better be higher than the other one. So if we wanted to plug in the numbers that we've got here, we're essentially trying to find K2 given K1. So the original K1 that we had was listed as 0.22. We were also given an activation energy of 300 joules per mole. So then that gets divided by our friend the gas constant times T1, which the original temperature was 298. 1 minus 298 over the new temperature, which is 375. Assuming I did the math there correctly, please check me. 2255. The units don't change. Liters per mole dot second. So at the very least, if I messed up something, hopefully it wasn't the signs, because my K went up. And I would expect the K to go up if I change the temperature in such a way that the temperature goes up. Yeah. C. Yes, positive. I think positive. I don't know. Do the math. We'll find out. No, I mean not like you do it right now. I mean we're going to look at that equation right now and check the math and see which way that it goes. So the A's cancel. And then if we take the log of both sides and factor out the EA, we would have minus EA over R times 1 over T2 minus 1 over T1. Right? And then we factor out the 1 over T1, which means this becomes that, and this becomes T1. And then we switch the signs to reverse them. So yeah, it should be plus, like that. Isn't algebra fun? Sorry, I'll leave that up there for a minute in case anybody missed it. So we use that expression to adjust it, which is good because I have the correct one here. And that's how we change K. I could have done it the other way around. I could have given you an A and an EA, and then you would just dump this into K is equal to A times the exponential of minus EA over RT. But this one's, I don't know, they come in about equal quantities, so it's not like there's really one that matches, or one that exceeds the other. It just depends on what the problem says. Both of those become really important when, again, we talk about non-isothermal reactors. So if temperature ever changes, you have to use something like this, because the rate constant will change. The next step was to ask for Ca as a function of time. Since it's a liquid phase reaction, we're going to assume that the volume is constant. If you ever see liquid phase, always assume that V is constant. And as a result, we can skip right to this form of the material balance, which is dCA over dt has to be equal to R sub A. We also know the form of that R sub A because we were told that this reaction was elementary. So if the reaction is elementary, minus RA has to be equal to the rate constant K times the product of all the concentrations of the reactants raised to their stoichiometric powers. So the only reactant we had was Ca, and its stoichiometric coefficient was 2. So that's our rate law. So that check that I said about units, this is always where I end up checking my units because I usually know 2 of those units. So if I want to check those units, the ones on the left always have to look something like moles per liter per time. So I just pick mole per liter per second. It could be mole per cubic meter per hour or something like that. You can adjust them accordingly. Those have to be equal to the units of K times the units of whatever comes after that. The units of Ca were given as mole per liter, but that's going to be squared. Because according to that rate constant, or that rate law, we have a square right there. So if you rearrange each one of those, you end up having a liter over mole dot second for K. It's a good check to have because they're not always consistent. I mean, K may be consistent by itself for that general form of RA, but the units of, for example, volume in K may not match the most natural units of volume for Ca. Right? Your Ca calculation, if you calculate it from like the ideal gas law or something, depending on which R you use, you might have like moles per cubic meter. And so you need to check those units to make sure that everything's working out pretty well. Remember, keep in mind that the one that's fixed is this one. The units of RA always look like amount, or moles, whatever those happen to be, amount per volume per time. Exactly what those are can vary, but it has to be some combination of amount per volume per time, always. K is the one that varies because the stuff on the right-hand side will also vary depending on what the rate law is. So that's our differential equation. We need an initial condition. In this case, Ca naught was equal to 1, specifically 1 mole per liter. So we put all that together and do the integration. What's worse for you? Let's see. Raise your hand if you prefer me to erase stuff on the screen versus go to a new screen. So raise your hand if you prefer erasing. Ain't nobody prefer erasing. Okay, going on to the next screen. If we substitute all that stuff in there, what we end up with is DC. Is it because you can't erase on yours? Might as well just go to another one. Works for me. The result of that integral, if we separate it, will be something like this. So where did that negative sign come from? This particular one? That negative sign came from the rate law. We almost always write it in terms of the degradation of whatever our reactants are. So if you look on that previous page, I didn't write RA is equal to KCA squared. I wrote minus RA is equal to KCA squared. Just the standard way that we write that sort of thing. If you end up integrating that, again, assuming that actually, if you want to integrate that and see what all the limits are, remember the limits for time goes from 0 to t, and the limits for CA go from CA naught up to CA. So if I want the expression for that, I can get CA as a function of time will be equal to 1 plus KT to the minus 1. This is another place where I always check my units, right? You should always be able to figure out that whatever's on the right-hand side has to have the units of the left-hand side. The left-hand side, we know what the units are over there. They have to be moles per liter. This has to be moles per liter because our initial CA naught was moles per liter. So we're always going to scale it with the same set of units. If we look at the units on the other side, this looks like it has units of a 1 plus a K, which K had units of liters per mole dot second, times a time, which has units of seconds, and then it was inverted. It looks kind of weird, right? Because what we've got is a 1 plus a liter per mole to the minus 1. That's initially wrong, right? A 1 has no units on it, but the liters per mole has obviously units of liters per mole. The problem here is if you write it like this, I've already substituted that CA0 it has a numerical value of 1. So there's a term floating around on the inside next to the 1 that's actually liters per mole. So when you're doing this sort of math, try to leave it in the form of variables as long as you can so that you can keep checking your units along the way. These units here should end up being just fine. But if you don't leave them in terms of variables all the way through, you can end up with situations like this where it seems like the units didn't quite work out, but if you track that math through pretty carefully, it should be okay. So generally, I would recommend actually writing this in terms of CA0, so leave the CA0 inside here somewhere. And then only when you're all done and you check the units of your final expression, put CA0 is equal to 1 in there, and it'll save you a little bit of a headache with units. So the thing that I'm mentioning here, this is actually, it's not just 1, it's 1 over CA naught, which does indeed have a numerical value of 1, but it also has units of liters per mole. It's a little easier to see how the units work if you had left that CA naught inside there. I think the actual question was figure out what CA is at t is equal to 10, which just means you plug that inside there, and you should get about 0.3. Right, so that's a pretty standard approach. There's lots of variations that I can give on that. Obviously, the rate law can take a couple of different forms. There's a limit, though, to what I can really ask you on this, because if I ask you to integrate that, you need to be able to integrate it by hand. If you want to know what the limits are of the kinds of things that I can ask you to integrate by hand, look in Appendix A of your textbook. So Appendix A shows you all the possible forms of an integral that I could ever give you. And I will give you those forms that are in Appendix A so that you don't have to try to come up with them on your own. So about the highest they ever get is like a polynomial. If they're beyond a polynomial, then I would ask you to, for example, set up but do not solve the integral. Something like this, I would expect you to be able to integrate something like that. But if you want an idea of the kinds of things I would ask for in terms of integrating things, check Appendix A. That's about as complicated as they'll get. And again, if you need one of those forms, I will give you those forms on the exam. Also a good kind of red flag, right? If you get an integral that you apparently can't solve that is not one of the ones that I gave you in the forms on the exam, you probably made a mistake somewhere. Or I made a mistake. The last part of this question was, I believe, to get XA. And so XA is the same kind of XA that we've had previously. It's 1 minus CA over CA naught. Or written another way, CA minus CA naught over CA. or written another way, Na minus Na naught over Na naught. All of those are fine. And if you do something like this, you should end up with 60-something%, about 69%. How do I check something like that? You can always do the other version, right? We said we can always set up the expression as dCA dt is equal to Ra at constant V. We saw there was an entirely equivalent definition that was dxa dt was equal to minus Ra over Ca naught for the same conditions at constant V. So you could approach this problem in either direction. If, for example, all I had asked you for was the conversion after a certain amount of time, you could use either one of these expressions and you should end up with the same answer. The only reason that the XA can occasionally be more useful is sometimes if the math works out in just the right way, you don't need to know what the initial concentration Ca naught is, and that makes the math here a little bit easier. You'll still end up in the same answer of X naught depending on Ca naught, regardless of which one of these you choose. It's just the cranking all the wheels of the math might be a little bit easier on the XA one. So very frequently you're going to see us solving differentials in terms of XA, simply because the equations that we're solving sometimes look a little bit simpler. But in this particular case, you could have done either one. So that's one thing that you can try. I have a little bit note here. One thing is try to get exactly that same answer, or even exactly that same expression that we had seen previously, using this particular form. Another thing that you can try, and this is something that we'll practice tomorrow, do exactly the same thing in MATLAB. So you should be able to solve this entire system in differential form without having to actually integrate it by hand or use any of the integral tools in MATLAB. MATLAB can solve that differential directly without a lot of trouble, and you should get exactly the same thing. The only problem with that, it can be a little tricky to find out what's the comparison I want to make. So you could, for example, plot this stuff. You could evaluate it at certain time points. Usually plotting is the most useful one that I go to. But you can try either one of those with this particular example, just to get a little bit more practice with doing the same thing in different ways, because they have to give you the same answers. Tomorrow's example that I had planned for in class was to actually do that in MATLAB, so hopefully we'll have enough time to get to that. We're in pretty good shape in terms of where we're going from here on out. Any questions on this stuff? K is one of the, or lowercase k, the rate constant K is one of the ones where we're kind of done. That's as far as we ever take the rate constant K. We're going to introduce another one now and then immediately get rid of it because it's not very helpful, but you still need to know that it's there. So any questions on anything up to this point? You can always interrupt me too. I mean, not always, but if I'm talking in a lecture and you're enrolled in the class, you can interrupt me. Reversible reactions. So those examples that I had just given you where we were doing them by hand, those were all examples of irreversible reactions. Typically, real reactions oscillate between, well, oscillate's a bad word. There are special ones that actually oscillate. They go back and forth between reactants and products. So there's some reaction that gives you products, and then there's some reaction going the other way that takes those products and turns them back into reactants. This is when those two rates are balanced, when the rate of things going from reactants to product is exactly balanced by the rate of things going from products to reactants, that is a state that we call equilibrium. So this equilibrium is a little bit different than, like, wait for it. This is also equilibrium. This is what we call static equilibrium, where the pen is just sort of sitting there, it's not moving. Nothing is really happening. If we zoom all the way into the atomic level, The molecules in the solid are jiggling a little bit, but they're not really moving from place to place. They're pretty much stuck in place. This kind of equilibrium is a different kind of equilibrium, and we call it something different. Whenever you have forward rate is equal to backwards rate, this concept is called dynamic equilibrium. Dynamic equilibrium. So it's not that the molecules have stopped reacting. It's not that we ran the thing long enough and we made all the B we're ever going to make and we made all the A we're going to make, and now nothing is changing. It's constantly in a state of change of the products going to the reactants and the reactants going to the products. This happens both in chemical equilibrium, which is a form of dynamic equilibrium, as in for reactors, but also for phase equilibrium. So if you have a droplet in equilibrium with its vapor, it's not that things aren't happening anymore. If you zoom into the molecular level there, you've got droplet or molecules of water leaving the liquid phase and molecules of water condensing from the vapor phase into the liquid. The reason that the macro scale doesn't change is because the rates of those two things happening are about the same. They can fluctuate on very short time scales, but on anything approaching a macroscopic scale, they're essentially constant. So that concept of dynamic equilibrium is a little bit different from the normal types of static equilibrium you might be familiar with. The rate constant that we assign for things going forwards from reactants to products is K sub F, and the rate constant for things going backwards by the reverse is K sub R. Those are lowercase k's, not uppercase k's. For the general reaction of, actually let me put this on the next page. We write the rate constants for these things in the same way if the rate law is elementary. It's just now we essentially have two reactions instead of just one. We have one going from reactants to products, and then we write another one for products minus going to reactants. So for the general expression of AABB goes to CC, oops, B, goes to C plus D times D. If this reaction is elementary, we write this rate law in a very similar way. We would say minus R sub A is equal to the forwards rate constant, Kf, times the concentrations of the reactants raised to their stoichiometric coefficients, minus the reverse reaction rate constant, K sub R, times C sub C raised to the C, and C sub D raised to the D. The only primary difference there is we've added this negative sign because the reverse reaction rate is generating A, it's not consuming A. That works too for partial pressures. So we saw earlier that we could have had, instead of CA, we could also have partial pressure of A raised to the A, partial pressure of B raised to the B, etc. The form is the same. The rate constants will be different for each one, but it works for either one of those. This term, the first one, we would refer to that as the forward rate, R sub F, and the second one is R sub R, the reverse rate. Some people use backwards or -1 or something like that. The forward rate is saying what's the rate at which the reaction is moving forward as we've written it. If you ever end up with really weird signs, it's probably just because the reaction is actually going in the other direction. But at any rate, when you have equilibrium, those two rates are equal. So R forward is equal to R backwards or R reverse. Again, they're not zero. You still have things going forward and you still have things going backwards, but the net rate, R sub A, the overall rate of production of A, is 0. That is 0 because the forwards rate is equal to the backwards rate. And so we can get something a little bit interesting, which is that the ratio of K forwards over K reverse looks like C raised to the C. That's kind of a weird, well, that's what it is. C sub D raised to the D C sub A raised to the A, C sub B raised to the B. That kind of looks familiar, right? We've seen expressions that look like that before, where we have the product of a bunch of concentrations of various species raised to their stoichiometric coefficients. If you don't remember what that used to look like, we would write that as the product of C sub I raised to nu sub I. We have a name for that one too. That's another capital K that we call K sub C. That's a new K sub C. We haven't seen that K sub C, that particular K before, but it's directly related to all the other Ks that we've known. Also, if you rewrite this expression in terms of the partial pressures, as I've done here, and you do that exact same thing, you'll end up with this, which is just K sub P. It's the same K sub P that we've seen before. So if the rate's written in terms of partial pressures, you get exactly one of the Ks that we've seen before, which is K sub P, which is why sometimes we write gas phase reactions in terms of partial pressures. It makes that link between the two a little bit easier to make. We can still make that link if we write our reaction rates in terms of concentration. It's just we need an extra step along the way. But either one of those are equivalent. I mean, I shouldn't say equivalent, they're similar, because they're relating a forwards and a backwards rate constant to one of the equilibrium constants that we've already seen. As a result, because we can establish this kind of a relationship at equilibrium, we usually use that to replace the K sub R. So instead of writing this K sub R, we would prefer to write K sub C or K sub P. The reason for that is because we have an independent way to figure out what K sub C or K sub P is, which is everything that we learned in week 1. Doing a whole other experiment to figure out what K sub R is usually not very good. It requires a lot of time and a lot of money, whereas something like measuring another KC or a KP isn't really something you have to do. All that data is tabulated already. So most of the time you will not see the rate law written in this way, even though that is exactly what we mean. We mean that there is some going forwards and some going backwards. What you will tend to see instead is the following. You'll see minus R sub A is equal to a rate constant out front. It is technically the forwards rate constant, although you will not always see it. Concentration of A to A, concentration of B to B, minus concentration of C to C, D to D, over that that equilibrium constant K. That's the much more common way that you will see that particular expression written, and it's one that you should keep in mind. Almost any time you see a reversible reaction, we're probably going to assume it's elementary, and so that's what the rate law is going to look like. Keep in mind the other one still works too. It's just got a different K inside there. So if you want to write it in terms of partial pressure, this is partial pressure of A raised to A, partial pressure of B raised to B, minus C to the C, D to the D, divided by K, but now the equilibrium K that you're talking about is K sub P. Which, there's a nice pattern to that, right? If you write it in terms of CA, then the equilibrium K you need is the one that has the C in it. It's KC. That's not a coincidence. We write it like that on purpose. So if you have, for example, a liquid, there's really only two options here. We're either going to deal with liquids or we're going to deal with gases. And we need to be able to figure out what KC and or KP are for both cases. The P one, this one, that's always for gases. This one, though, you can see that one written for either gases or liquids. The question for both of those is how do we relate them to the other K that we already know, which is just the normal K, right? The equilibrium K that we can get presumably from something like the full Van't Hoff equation, where we would have K0, K1, K2, right? Because we can calculate that stuff. We can put it into KCalc and figure it out. The relationship between those two isn't terrible, but it does take, I guess, a little bit of bookkeeping on your part. So let's take care of the liquids first. Remember, the idea is we want to establish what K is and how it relates to the other two. For liquids, we had seen that K was always equal to Kx. That was our original condition for liquids. It was always equal to Kx. Kx we had defined as pi, which is the product of all the mole fractions raised to their stoichiometric coefficients. The step that we have to take in order to relate this to something else is to recognize that x sub I, the mole fraction in the liquid phase, is equal to the concentration I divided by some total concentration, which is the same as saying the concentration of I divided by the total number of moles divided by the volume. So as a result, that pi term looks a little bit different, and now it's Ci over this C sub t raised to the stoichiometric coefficients. And if you work each one of those out, that ends up looking like the Kc that we saw before times this Ct parameter. Actually, it's not really a parameter, right? It's just the total number of total concentration that's there, total number of moles divided by V. And it's that term raised to the sum of the stoichiometric coefficients. Conceptually, that's very similar to the relationship we had between Kp, Ky, and P raised to the sum of the stoichiometric coefficients. If you flip back in your notes to like day 3 or 4, you'll see something that looks really similar to that, except instead of Kc times Ct, it's something like Ky times P raised to that same sum. So they're very similar. So that's the link that we make between the two of those for liquids. For gases, the relationship we saw for gases was that the equilibrium constant K was equal to equilibrium constant K sub P. You may be done right there, right? If your reaction rate was given in terms of partial pressures, you're done. You don't have to go any further. We already know how to handle that particular Kp. If your reaction rate was given in terms of concentration, as it, I don't know, 50% of the time it is given in terms of concentration, that's okay. Your K sub P was defined as your partial pressure of all species I raised to their stoichiometric coefficients. And so we use our good old friend, the ideal gas law, which says that the partial pressure of any species I is equal to its concentration times RT. And so as a result, you get the product of all Ci times RT, RR, raised to their stoichiometric coefficients. And this ends up looking like capital Kc, so equilibrium constant K in terms of concentration, times something else, which is the product of RT raised to the sum of the stoichiometric coefficients. So there's a lot of forms that look like that, right? Some kind of K that we can work with times something raised to the sum of the stoichiometric coefficients. Until you get really comfortable with it, just keep a little table everywhere that says there's only about 3 of these that I can do. There's a K is equal to Kx that leads to this for liquid. There's K is equal to Kp that leads to this for gas. And then there's the plain old Kp for a gas if everything was already written in terms of pressure. If you have a mixture of the two, like a liquid phase reactant and a gas phase product, God help you, because it's awful. We're not going to deal with any of that. It'll always be one phase or the other. So tomorrow we'll go over an example in MATLAB of this stuff, because you're going to start needing MATLAB a ton on your homeworks. So we're going to try to go over an example of that.